Hello everyone, myself Shefa Shah from ICT department. Now in yesterday's lecture of microprocessor and microcontroller, we have started our unit 4 and in this we have discussed about addressing modes of AVR, right? Now and data transfer instructions of at Mega 32, right? Now in this unit we are going to start, this topic is related to arithmetic and logical instructions related to at Mega 32. Right, so let's get started with arithmetic and logical instructions with at Mega 32. Now, as you can see in this, these are the listed logic instructions in our assembly language programming of at Mega 32. So these are the first, that is A and D. A and D, what it will do, that it will logically AND the content of two registers, right? Then A and DI, what does it will do? So it will AND immediate, that means it will AND logically AND the content of one register and one immediate data along with immediate data. Then OR, that is OR, logical instructions or logical OR between the content of two registers, right? Then ORI, that means the logical OR immediate with immediate data and the content of one register, right? Then EOR, what does the EOR will do? That is exclusive OR, right? So it will exclusive OR will do the XOR operation between the contents of two data. Then COM stands for the complement. So complement will do the it is a one register instruction, right? And one register, it will only have the one register, and what it will do, it will complement the data, means if it is a 0 then it will become 1, and if it is a 1 then it will become 0. So the COM instruction will provide us the ones complement of the register content of the register. Clear? Then NEG. So what this NEG stands for? Negate. So negate will provide us the truth complement of the content of the register. Clear? So then DEC. So DEC, that will be decrement the content of register by 1. Then CLR. So it will clear the content of the register. So whatever the register will contain, it will clear and it will have the data 00H. Right? And last SER. So SER will do set the content of the register. So whatever there will be a data in register, if the SER instruction is used, then particular register will have FFH data. That means all the 8 bits will be equal to 1. Clear? So these are the logical instructions. Now we will see each and every logical instructions in detail with example and its syntax. Right? So let's take first example, first logic instruction, that is AND. So A and D, that means logical AND, right? So logical AND between the two content of register. So the syntax is A and D, RD, RR. And the flags affected are Z, V and N, right? And the example, let's take an example. So AND R21, R22. So as you can see in the below figure, the R21 has data 53H, which is represented over 5 is represented over 0101 and 3 is represented as 0011. Then R22 has data F0. F stands for 4 ones and 0 stands for 4 zeros. Now we will do, what we need to do is we need to logical AND between these R21 and R22. So as you can see on from the LSB, first bit, that is 1 0. So a logical AND of 1 and 0, that will be equal to 0. Right? Again 1 0, second bit, that is 1 0 to 0, 0 0 0, 0 0 0. Then 1 1, that will be equal to 1, 0 1, that is 0, 1 1 equal to 1, and 0 1 is equal to 0. So after the execution of this instruction, what it will do, it will provide the logical AND operation, and the result is obtained and the stored in destination register, which is R21 in our case. So R21 will have data 50H in the execution after this operation. Clear? So this is the first instruction, which is AND. Then second instruction, which is A and DI. So what does it will do? It is same as AND instruction, but in place of two register, it will only provide one register and one immediate data will be provided. Right? So the syntax is A and DI RD, K, where small k stands for a 8-bit number, which is again in a hexadecimal, which is directly provided with the AND A and DI instruction. right? Again, the flags affected will be Z, V, and N. Now let's take an example, that is ANDI R21, comma 17H, right? So the 21 has data, that is again what we have taken, that is 53H, which is in the previous slide. So R21, that is 01010011, that is 53H, right? Now 17 can be displayed at 17, that is 1 will be displayed as 0001, and 7 will be displayed at 0111, right? So whenever we are obtaining an logical AND operation, then after AND operation, the data in R21 will be equal to 13H13, right? So it will be 00010011, right? So this is the data obtained after the ANDI instruction. This is similar to AND instruction. Clear? Now next, that is OR instruction. So in OR instruction, again the logical OR operation will be performed between the two bits, right? So the syntax is OR RD comma RR, and again the same flags affected, that will be Z, V, and N, right? Now let's take a same example, that is OR R21 and R22. So R21 has data 43. So 43 can be represented as 0100 and 00113, and R22, that is 10. So 1 is represented as 0001 and 0 is represented as 0000. So whenever we do a bitwise logical OR operation, we will have the data, that is 101, 101, 000, starting from LSB, 011, 001, 101, and 000. So after the execution of this operation, right, what it will happen, the R21 will have the data 53H. Clear? So this is the logical OR operations. Similarly, ORI, that is or logical OR with immediate data. So the same way like ANDI, this is a OR instruction with immediate data. So the syntax will be ORI RD comma K, where K is an 8-bit number, right? And again the flags affected will be Z, V, and N, right? So the same data we have taken for R21, that is the 53H, right? And it is represented in the first line in the below figure, right? And 17H, which is represented in the white line, that is 0001, 0111, right? And now when we logical OR this both operation, what it will happen, we will have the data 0101, 0111, which is, that is 57H in our case, right? So after the execution of this operation, that is ORI R21 comma 17H, the result in R21 will be 57H, will be 57H. Clear? Now next, that is EOR, that is exclusive OR, right? Now with the exclusive OR, that means XOR operation. What does the XOR operation means? That if both are ones or both are zero, the result is zero. If any of the if any of the data is 1, then the result will be 1, right? The syntax is EOR RD comma RR, right? And the flags affected will be Z, V, and N. So EOR R21 and R22, right? So let's take the data in the below figure, that R21 has D3H, right? D is represented as 1101, right, which is 13, and 3, that is 0011, right? R22 has data AA, that is 1010, A, that means 10 in hexadecimal. So 1010, 1010, right? So after the XOR operation, what it will happen, from the LSB, first bit is 10, so our result is 1. Then second bit is 11, so the result is 0. Then 00 to 0, 01 to 1, 10 to 1, 011, 101, and 110. So after the execution of this instruction, right, in which the data is D3 and AA in R21 and R22 respectively, right, the exclusive OR operation between R21 and R22 results in 79H, and which is stored in R21. Clear? Now next, that is logical instruction, that is COM, right? So The next logic instruction is exclusive OR. Right now, in exclusive OR, what the result will be, if the both input are 1, or if the both input are 0, then the result will be 0. If any of the input is 1, then the result will be, output will be 1. Right, so let's take syntax, that is EOR RD comma RR. Right, the flags affected will be Z, V and N. Right, and the examples are EOR R21 and R22. Right, so the R21 will have data D3. D3 is represented as 1101 and 0011, and R22 has data AA, so it is represented as 1010 1010. So after the execution of EOR, that is R21 and R22, the result will be 79H in R21. Right, so let's see how it is. So starting from the LSB 10, so it will be 1, 11, so it will be 0, 00, so it will be 0, 01, that will be equal to 1, 10 equal be equal to 1, 01, 1, 101 and 110. So finally, when we convert it into hexadecimal, we will have the result 79H in R21. Right, now next logical instruction, that is COM. So what does the COM do? So COM, that means complement. Right, so let's take the syntax, that is the COMRD. It is a one register instruction. Clear? So it will do one's complement of the data in the register. The flags affected are Z, C, V and N. Right, and examples are COM R21. So R21 has data. Let's take an example of R21 has data 55H. So 0101 0101. So after the complement instruction, what it will do? Complement will complement each and every bit. So if it is 1, it will convert it into 0. So after the execution of COM instruction, R21 will replace the data from 55 to AAH. Right, so this is the execution of COM instruction. Now next, that is the negate instruction. So negate instruction, it will provide us the 2's complement of the register data, and the syntax is NEG comma RD. Right, it is also one register instruction, and the flag affected are Z, C, V, H and N. Right, and examples is, let's take NEG negate. So negate, what it will do? It will, first of all, it will, R21 has data 55, so it is represented as 0101 0101. Right, now for 2's complement, what is the logic behind that? First we have to obtain 1's complement. So we have seen in the complement instruction that the after complement instruction, R21 has data AAH. Right, for obtaining 2's complement, we need to add 1 in that. So if we add AA plus 1, then what it will be? AB. Right, so after the execution of this NEG R21, the data in R21 will be AB, which is represented as 1010 1011. Right, so this is the negate instruction. Next, that is decrement. Right, so decrement will decrease the register contents by 1. Right, so decrement RD. Right, it is also one register instruction, and the flags affected are Z, V and N. Right, now the data in R21 is 55H. Right, so what it will have? 0101 0101. Right, now whenever there will be an execution of decrement R21, then the data is 55H, it is decremented by 1, so the data will be 54H after the execution of R21. Here, so this is the logic instruction, that is DEC. Then logic instruction SER, that is set register. So the set register will set the content of all register by 1. So when the syntax is SER-RD. Right, and SER-R21. So let's take the data is 55H. Right, and if we execute this SER-R21, then all the data will be equal to 1. So the data will be equal to FFH in the registers. Clear? So that's all for today's session. Here we have completed our arithmetic and logical instructions for ATmega 32. Thank you for watching.